Thank you for coming and being part of our class. This is engineering math class. This is lecture number 4 by Dr. Emanuel. We are doing series, complex series, and roots. So we're going to be looking at complex series, roots, and convergences. We would like for things to converge and rather than to diverge, so that it'll be going toward one number, it'll be going toward one place. And we can verify that by each number that consecutively happens after the other should be getting smaller. So as we have here, we'll call this A of n. The parenthesis for 1 plus I, that parenthesis raised to the n power, divided by 2n. And so what we have is we expect that the next number after this, which would be 1 plus the parenthesis 1 plus I raised to the n plus 1 power. And we would expect on the denominator that it would be 2 raised to the n plus 1 power. That number should be smaller than this number that we have in front of us. And so we're going to use the ratio test to test it, to see if these things are so. So, as you can see, we taken the absolute value of both terms. This is the A of n, this is the A of n plus 1. As you can see, wherever we had n, we added n plus 1. So it's n plus 1 on the denominator. And with the numerator, we have the term 1 plus j, that quantity raised to the n plus 1 term. And we have the 2's, 2 to the n here. We'll cancel out with this 2 to the n, and it'll just leave you a 2 on the bottom. And on the top, we will have everything. The 1 plus j will cancel on top. The only thing that'll be left is j plus 1. 1 plus j. Okay, now the next thing we want to be able to do, now that we have it in this form, we would like to find out what is the absolute value. Okay, we need the absolute value of the term, and that to find the absolute value, we have to multiply each one by its conjugate. Okay, so the first thing we want to look at is the conjugate. Okay, and the conjugate of 1 plus j is 1 minus j. Remember, you're only changing the imaginary terms. You are not changing the real term. Okay, so what we have here is when we finish multiplying them out and taking the square root of that, the perfect square, we should wind up with 1 squared plus 1 squared. The square root of that, which is the square root of 2. And so what do we find? We find when we put the 2 back underneath, this was just for the top. When we put the 2 underneath, we divide it by 2. And we can see that this is a number, that it comes to the square root of 2 divided by 2 is a very small number. And it's less than 1, so it absolutely converges. So, we're going to try another problem. We would like for you to try this on your own before you look at my answers. Okay, we're going to be looking at j raised to the n power divided by the square root of n. If you take your time, and then you can pause it and come back. Okay, so what we will do again, we will take the absolute value again, and we will be looking at the next term after the n plus 1. So as you can see, we are now dividing the a sub n plus 1, which is j n plus 1, divided by the square root of n plus 1. We're dividing that by j n divided by n square root. Okay, so we can see here that the j's, j to the n's will cancel, and all we're going to be left with on the top is a j. The square root of n will come to the top because it's dividing, and the square root of n plus 1 will stay. And so, as you can see that as you go higher and higher, into the millions and billions, that the number n will be very insignificant because they'll cancel out, and that'll put you at basically j, or at 1. And so at that point, we cannot make a decision on if this is convergent or divergent, because it must meet the condition that it has to be less than 1. It can't be greater than 1, and it can't be equal to 1. If it's equal to 1, we need to go back and do another test. So let's try another test. What would be a good test? Now you can see these are alternating numbers. We have a plus j, a minus 1/2, minus 1 square root of 2. Then we have another plus to j over 3. And we see that this is constantly changing. So since it is constantly changing, the alternating series would be a good one to use. Okay, so we'll use the alternating series. And as we use it, we'll be able to see here that these numbers are changing for the real and the imaginary part. And so every so often, we have to verify what is actually going on. So we can see that we still have to take the absolute value of this. And as we do, boom, 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 we can get a number. If you notice, every time it's just a number, a j, or a 1, or a negative 1, or a negative j, or a positive j. That's all it is. And each time we have that, that's divided by a number that is very high. So that means that what? The number on the top is not going to change. The number on the bottom keeps increasing. So that means that it will be convergent. Okay, now we're going to look at the disk of convergence. Now we're looking at disk in reference to area of circles and circumferences and those type of things we will be looking at. So the first one we want to look at is z to the n. That has an origin. Its center is in 0, 0 origin of where it is, of where all the numbers that will affect this particular function. Now we move it to another one, and we'll see that it moves by 1/2. Z minus 1/2, and so when you take it to 0, the other one you set a 0 in there, that means it was 0. Okay, this one, when you set a 0 in there, to get a 0 for z, you have to do what? You have to add what? 1/2. So we're going to shift it by 1/2. So tell me what you think is the next one. The next one, yes, what would you do? Yes, it's going to be shifted. You have to add an I, a positive I to it, and so you shift it up so that it can go to 0. Okay, now the one on the bottom, you don't have to do anything with it because it's already at 0. It's also at the origin. Okay, so now we have the first one we would like to look at. We see that this is the equation that we're using for finding the absolute value is the same formula that we're using for a circle. So I hope you can see that. X squared plus y squared, that whole quantity, that group of things. So what we have here is the circle centering on 0. So what is our next opportunity? Is that we are able to see that we can shift it by 1/2, and when we find out what is the root or what will cancel out here, we set this to 0. Only way we can set this to 0 if z equals 1/2. And when z equals 1/2, that means x is going to be moved on the x-axis by 1/2. And this is similar to another circle, but the circle is shifted. But as you can see, it's still the same format. The circle is shifted by how much? by 1/2. On what axis? On the x-axis. Okay, we hope that you're getting this. Now we have, instead of a positive number shifting it, we have an I, an imaginary number shifting it. So we're going to shift it going up 1. Like I said, you're going to add a I to this, and bring it to 0. And if you do that, then you're shifting your circle up 1. Okay? So if you take the absolute value, that's what would happen. And as you can see, the form is the same form as a circle, just shifted over the y-axis, or over the imaginary axis. Okay, so the next thing we like to look at, we like for you to look at this problem. You can work it, and then pause this, and then you can come back and compare your answers to the answers that we have here. Okay, so we're going to use the ratio test again. Okay, by using the ratio test, remember, we're taking what the actual series is, and we're going to compare it to the next term, the n plus 1 term. Okay, and we're going to divide it by that. We're going to divide the smaller number, or keep it on top, into the larger number into the smaller number. And so, what do we have? We have here the n plus 1 term divided by the regular term. And what we're doing here, we can cancel some of the terms. The n factorial, they can just leave an n plus 1 there. And then the I to the z versus I to the z minus plus 1, that we will have this go to 1. As you can see, we just have z, and the only thing that's increasing is the denominator. And we can see the denominator is racing toward what? Yes, 0. So because it's racing towards 0, that means what? That means that it converges, because now p is less than 0. Remember, if it's greater than 0, it's diverging. If it's equal to, if it's equal to 1, you cannot tell. If it's greater than 1, it's diverging. And this is good for all z. Okay, so next area that we would like to examine is getting terms, getting everything in these specific terms and formats. Okay, so if we have anything just z raised to no power at all, it's just a regular form of e of r times e to the I theta. But now, if we're going to add a power to that, then it's going to be, we multiply it times everything in the exponential. So r gets an n, and e gets an n also. And we find out that we also have to add that to our sine and cosine. We're multiplying it times that angle, such that it can move that much rapidly. Then we have the 1 over n, same pattern. People are thinking that as we move forward here, we will see that we have the cosine and the sine. The angles are multiplied by n, not just the absolute value is raised to a specific power. Then we have, if you are taking the root of something, then you divide by that specific root. You divide the absolute value, and you also do that to the angle. And when you change it over into sine and cosine, you divide your angle by that amount. Okay, we have steps we need to take when we're finding roots, as we've been walking you through them. Find their polar coordinates of the root, take the nth root of r, and divide the theta plus 2 pi k by n. Also, you want to make a sketch and draw a circle of the radius so you can make sure it's in the right quadrant and that it makes sense. Also, you want to plot the root with the angle n, and then plot the rest of the n roots equally around the circle. Okay, we're going to be taking the root, the cube root of 8. Taking the cube root of 8, remember we said if it's taking the root, but we divide by that root. Okay, so like I said, practice it and then pause it, then practice it, then come back. Okay, this is n is now 3 here, and r is what? 1 over 3. And so what we have here is that we had the circle and we had 3 different points that we were going to. Okay, so we can see here we're just going to plug in our regular formula with the 3 to 1/3 times everything. Then we're going to put in the sine and cosine as it's divided by the same 3. Then we're going to see that r is equal to the cube root of 8. Okay, and so since r is equal to the cube root of 8, there's only one solution that's real. That means there has to be 2 others that are not, that are imaginary. And so that's what we so that's what we've been able to find out. And so what we see here is x is equal to 2 when y is equal to 0. So that's the one root that's actually coming out. Okay, so as you can see, this will be this particular one at x equals 2 and y equals 0. Okay, so there's 3 roots because it has this root of 3. If it's root of 6 or 10 or 20, those are how many roots it has. Okay, we need to try to find them out. And if anything, we can circle around by adding 200 and by adding 2 pi, or what we call 360 degrees. Okay, so the next step that we're taking, we know what r is, okay, and now we should be able to move to the other 2. Now, how do we move to the other 2? We divide it equally, we said. Okay, so we see this one is here, and the other ones is 1/3, 2/3, which makes sense. So as you can see here, this is just theta, then this one here is what? Theta over 1/3, and then this is what? 2/3 theta. Okay, that is being used. And also on the outside, the magnitude is still 2. That remains constant. And we pray that you might be able to be receiving this and that this might be working out for you. Okay, so now we're going to look at another one. We're going to look at the negative square root of 64. Okay, cube root of 64. All right, same rule. So I want you to go home and practice it and then come back and check it out. You can pause the video. Okay, so now what we're going to do is we're going to look at this 64, and it's this 3rd root. So what we want to be able to do is put it in the correct format. That is all that we're doing. And as you can see over here graphically, that there are 6 different points of connection. And so what we'll be doing next is being able to use that rule that I shared with you all. Okay, so as you can see, we're just plugging in the 1/4 into the appropriate places here. Everything is being multiplied by 1/4. Okay, so the next one, we see that we have it in the sine and cosine, and that the angle is divided by 1/4 again. All right. And as you can see that you can take the square root, the fourth root of minus 64, and you come up with this 2 times the square root of 2. Okay, so that's one of the points in space. Okay, then we're going to take it again and put it back in its general form. And from its general form, we will be able to move on to the next sector. Okay, the next sector that we find here is that the 2 divided by the square root of 2, 2 times the square root of 2, that is our r. And that's what we're going to be using for r. R is going to be that number out front, and then we're going to divide by 1/4 each of the angles. And so you'll see here now, that'll be over pi over 4. And then what do we have after that? Then we add on again, and instead of just pi over 4, we're going to have 3 pi over 4. And then when we go to the next one, the last one, which will give us that part, will give us 5 pi over 4. Okay, so that is where we are at this point. Okay, and as you can see, each one of those are divided by that. Okay, so we move to the last one, which is 7/4 of the angle of what it will be surviving. So it's 1, 2, 3, 4. Okay. All right. So as you can tell, we're just adding up what? 1/4, and then 2/4, which is 3/4, then 5/4, and then 7/4. Okay. So now we talk about trigonometric and hyperbolic functions. These are basic principles that we just need to have. As you can see, we've been using in the past already the exponential, and we've been using it with the cosine and the minus sign. And we have the exponential as it relates to a minus I theta, okay? And now notice what has changed. The only thing that has changed when it's positive, only the sign changes. Why doesn't the cosine change? The cosine does not change because the cosine doesn't matter what side of the graph it's on. It's symmetrical, so it doesn't matter. But with the sign, it does matter. Depending on where you are, it'll be the reverse sign. So that's why the sign gets the negative sign and the cosine does not. Okay, so we can see here that this is one of the rules. These are formulas that we'll be needing, that we'll be using, that will be useful to us as we go through this journey. Okay, so now we have the hyperbolic, okay, as the imaginary term. As you can see, the sign of I in imaginary. And now this is also another term we should know about. Not saying that this is what we have to do or that we will be using it, but these are some terms that will be useful. Then we have the hyperbolic, as you can see down here at the bottom, for the sine and for the cosine. Okay, so the next one we want to move to, we know that the natural log of an exponential is equal of x is equal to x is equal to whatever it is. What about the log of z? Okay, the natural log of z, you can do the same thing. When you have the natural log of z, you have the absolute value times the e to the I theta. You can break this up, so you can now put the natural log of r by itself and separate the e. Okay, and now you know that what? We already mentioned that up here, that the log of the of e, it will give you x, so the natural log of e to the I theta is going to give us, guess what? I theta. Okay. However, remember that theta is not unique. It changes. All right. We're number 0.9. We're number 0. We're what? We're e raised to the power of pi 2 I squared. Really? Wow. Okay. So, we have here that we have an AC circuit, and we like to know how we go through this AC circuit. Okay, so what we want to do is be able to find the voltage of an AC circuit. Okay, remember, an AC circuit, if we find voltage, is the voltage if you have them all in series, which this is, which is good, you can just add them up. Okay, so this is a simple one. Okay, so how do we know this works? Okay, these are the differential equations for the LRC circuit. Now, you might have had a little bit of it, but I don't think you had an LRC circuit. I think you had an LR and a CR. I don't know if you had an LR circuit together, all three of them. Okay, but now we are having all three of them. And this is what the differential equation looks like. The differential equation is in this format. Okay, and this is what you remember. The voltage of the inductor is always J omega L. Okay, that's what we usually use, J omega L. Then what about for the capacitor? For the capacitor, it's a minus 1 over J omega L. Say it again. It's 1 over J omega C. But now when you flip it and put it on the top, it turns into a negative, and we're going to see that. I'm going to walk through each of these steps for you. Okay? And we know that for the voltage, it's just for the resistor, it's I times R. Okay? And notice, this is the only one that has the sign. The other two have the cosine. Okay, you try it yourself and see if you can derive the equation. Okay? So, let's start trying to derive the equation. Like I said, you can pause it. But if you want to hear it, it's okay. So, with this particular one, what we're doing here is we have the current of, it's dependent on time, it changes in time, and we can see that it's the initial current times the sine of omega t, okay, and that changes. Okay, now we're going to convert this to E. We said that already. Okay, and using Ohm's law, we know that voltage is equal to I times R. R does not change, so that's what we don't have to worry about. So, what about inductors? Okay, the inductors is going to change. So the voltage for the inductor is L times dt of I at t. So it changes with the current. Okay, so how do we find what the voltage is? We're getting rid of this differential. So to get rid of the differential, we have to take the derivative of I. Okay, let's go back up here and see what I is. This is what I is. Okay, what is the derivative of I? Okay, I, okay, it's a reference to time. So I naught stays the same, okay? That doesn't change at all, okay? What is e to the I omega t? Okay? If it's only about t, that means that it's I omega. Comes down, so you have the L that's still there, that's a constant, and you have the I omega. Okay? And then when you take the derivative of it, it's still back to what? E to the I omega t. Okay? So this is what you have. So this here is again what? Nothing but what? The current. Okay? So basically, just as I mentioned to you earlier, you'll remember it. I or J omega L times current is your voltage. Okay, let's develop it for, guess what? Aha! Yes, the capacitor. Okay, so for the capacitor, what do we have? We have here, the formula is dV over dt equals 1 over C. Okay, so to get rid of this dV, we need to integrate. We need to find what this voltage is. So what we're going to do is we're going to integrate, okay? And we're going to move some terms. We're going to take this dt and we're going to put it on this side of the equation. As you can see here, we're going to take this dV and we're going to integrate it. So if we can integrate dV, we'll just get what? V. Yes. Now then what can we do with the 1 over C times the I t dt? Okay, so we have to integrate this I dt again, just like we did up here. Okay? So, here we go. The Vt, okay, like we said, we took the derivative, took the integral of this derivative, and it gives us Vc, okay, and we've taken the integral of 1 over C of this particular I, okay, that's I-O, initial current, and it's E raised to the I or J omega t times dt. Okay, there should be a bracket here separating this. Should be an equal sign here separating this. Overlooked. Okay, so we have this here. When we integrate this, okay, when we integrate this, we have C. And what happens to the C? C is just a constant. It stays out. What about the I-O? Okay, the I-O just comes out. It just stays out. That's all it does. Okay, what about the I omega t? Yes, the t, again, will transform. Okay, so we divide it by what? I omega. Okay, so now you have I omega c. C was already on the bottom. Now you have I omega c on the bottom. Times I initial, and this is raised of E raised to the I omega t. Okay, so since it's here raised to I omega t, this whole thing here is nothing but what? What we started with, the current. So remember, for your circuit of a capacitor, the differential equation is 1 over I or J omega c. That's how I remember it. That's how I remember it. Okay, so now, what else can we do? Can we break it down a little more? Yes, we can. Therefore, V is equal to V of R, which we already talked about, I times R. V of L, which is where, let's look for this thing here. Okay, V of L is up here. Okay, there's V of L. Okay, J omega L. Okay. All right, and that's the R, and this is the I omega L. Okay, or everything's time IT. And then what is we said for the capacitor, the voltage for the capacitor? All right, 1 over I omega C. Okay, and all of this is multiplied times IT. Yes, so this is how you solve it. Yes. Now, hey, remember, we can't keep the J on the bottom. We need to move the J to the top, right? Remember, we can't have it of that form. Okay, so what we have to do is multiply I over I for this only one component. I times I is what? A negative 1. So here we go. We got a -1, and we have an I on the top, and we have our omega c on the bottom. This is the final form that you will always find these in. Okay? There's other systems that will be going on. There's systems that are riding the twister, the carnival. Okay? And so even system modeling. We have many system modeling that'll be going on. How would you model this? Here you have your R1 and your R2. Here you have your omega. Remember, we've been talking about omega, the angular velocity. Okay? So this is the general form. We have the real and imaginary of z. Okay? The real term and imaginary term. Remember, we see this as a negative number here. Okay, remember that. Okay, then we have the voltage, not the voltage, the velocity. We want to find the velocity and the acceleration. Okay, but for us to do that, what do we need? We need what the equation originally is. Okay, so what is z? This is the equation. Okay, and so what we need to do is take the derivative to find the velocity. Okay, let's take the derivative of this, okay? So if you take the derivative of this, what will you get? You'll be bringing down your I and your omega, so that'll be 3I omega, right? And this doesn't change. And down here, you'll be bringing down what? A -3 omega. Ah, there we go. See, there it is. See, just like I told you. Okay, so there's your 3 that remained the same. Your I omega came down. You had your negative. It was a positive, so now it's a -3I omega. Yes. And this stays the same, the exponential. Now, how do you find the acceleration? The acceleration of how fast it is moving, you take the derivative again. And there you go with your second derivative. Okay, and so what will the second derivative go be? Basically the same thing. You're bringing down what? The 3 doesn't change. You're bringing down the I omega, so it's I squared omega squared. And this stays the same. Now this one is a negative times a negative gives you a plus. 3 times 3 is what? 9. And now you have what? I squared and omega squared. Okay? So this is what we've been working toward. Now this will be working toward harmonics, harmonic motion. This is the differential equations. Notice what you do with this differential equation. You're taking the second derivative. Yes. Okay, and now if you have this as the first derivative, as this solution, okay, what is going to be your second derivative? Okay, you can plug x in right here, and what is your second derivative? Just like we just found out a few seconds ago. It'll bring down omega I, and this will stay the same. That's to be for your velocity. Then you take it for the second derivative, then it'll be I squared omega squared times this. See how simple that is? I know you can do it. You're a brainiac. Okay? Same thing with here. When we're talking about a spring, we're going to be taking what? The second derivative again. Well, I'm sure that you had a good time. I hope that you enjoyed our presentation with you. Now, remember, make a write-up of this, what you learned. Write down questions you have and things that's not clear. Okay? Thank you. And I will see you again in class.